Okay, so those of you who are retaking the Unit 6 test, it's important for you guys to know this. So if you're not doing that, it doesn't matter. But Unit 6, okay, here it is. There's a Unit 6 test. Okay, you're not actually able to see it, and maybe in Student View you can't see it. So let me come over to assignments, see how this works. Okay, maybe I can't see it because it hasn't been assigned to me, but if you retake the Unit 6 test, you're not going to do that. I'm going to leave Student View. And I'll go back to modules. What you should be able to see when you do the Unit 6 retake, and other people have done this already, so I know it works, but you'll be able to see Unit 6 version 2. You're going to be looking for that test to take. So you're not going to be, if you click on that one, it's going to say you don't have access to it, but this one you will on the day that you selected.
Is it going to be in Canvas again?
It is going to be in Canvas again, yes. Oops. So that is just a minor thing. I will go ahead and mention it now, though the very last thing we're going to look at today is more about the Unit 7 tests. So Unit 7 tests we're splitting into two parts. So part one is going to be homework tonight, and it's actually just completing your progress check. And we'll specifically talk about it. There's a certain progress check that I just assigned last night. You'll need to get that done tonight by tomorrow evening. And that counts as 60% of your grade, just getting that done, participation. So the baseline, assuming you do that, the baseline you can get is a 60% on this test. If you miss everything on the test tomorrow, so you'll have another part two tomorrow, which are actual questions that are multiple choice, and that'll be graded for correctness. So anyways, I will remind you of that before you leave today, but that is assigned already on Canvas. All right, so let's go ahead, and what we're going to be doing today is going over a bunch of problems from Unit 7, and I'm going to pick problems from these that we go over today that are similar, or sorry, that I'm going to edit, change in certain ways. And so you'll see some questions on the test tomorrow that look like these. So if you can understand these questions, you're okay for tomorrow. So we're now looking at the distribution of weights for a bull elk in a certain population, and it's approximately normal with a mean of 950 and a standard deviation of 60 pounds. What is the upper and lower bound of the middle 90% of the weights? What are the upper? What is the upper and lower? Oh, sheesh. That's English. I'm not an English teacher. All right.
Is.
Okay. Maybe I should say, what are the upper and lower bounds? I don't know. Let's model this question and figure it out. No. Okay. So really what's going on here, when I get this going, we've got, of course, 100% of all the cases underneath our normal curve, but we're only looking for the middle 90%. Now here's the 50th percentile right here. It's the 50th percentile because it's a unimodal symmetric distribution, and the median and the mode are the same. So somewhere down here is the lowest little bit, and somewhere up here is the highest bit, and we want this part in the middle to be the 90% of the data. All right, so now there's a couple ways you can go about doing this. You could probably just figure this out in your head, a lot of you, what these two bounds are. But one way, kind of a more formal approach to this, is you could take the 50th percentile and you could add this 90% right here divided by 2, which is 45%. So basically 50% plus 40%, sorry, 45%, if I can do math. So 95%. So this upper bound right here is sitting at the 95th percentile. Now the lower bound would be the same thing, just minus that 90% divided by 2. So again, that would be 50%, minus 45%, and then that would equal 5%. All right, not super complex right here. And so we can see that we want to find out the lower and the upper bound is going to be basically what's the 95th percentile of this distribution, what's the 5th percentile of this distribution. And that makes sense, of course. 95 minus 5 gives us the middle 90% of the data. Okay, so knowing that, I will create some room here. Oh, I'll just write on the left. If I want to figure out the 95th and the 5th percentile, first thing I need to know is what are those z-scores? So I'm going to have to do inverse norm, and I want to get the 95th percentile, which is 0.95 area with the 0 and 1, the standard model. And I'll do the same thing with the 5th percentile. And so I want to find out what those z-scores are. All right, so on the calculator, make sure you go to your distributions, inverse norm for your third. So 0.95 gives me 1.645. So I'm just going to put 1.645 right here. I know I'm squeezing this in, but that's where it is. Now, you can calculate the 5th percentile, but what you might be able to remember, because this is symmetric on both sides, it's just going to be the negative. So it's going to be negative 1.645. Of course, I do encourage you to actually plug the numbers in if you aren't 100% sure about that. So positive and negative 1.645. And now we're going to do some z-score calculations because it wants the lower and the upper bound for this particular distribution of 950 and 60 pounds. Okay, so that's going to be x minus the mean divided by the standard deviation. We know the mean is 950. We know the standard deviation is 60. And I actually know for the 95th percentile, that's 1.645. So I'm solving for x. All right, I'm not going to do any more stuff written down right there. But you can do the math on that. You can do the algebra yourself, and we can figure out what that x value needs to be. So it was 1048.7. So the upper bound will be 1048.7. Hopefully you guys are getting the same thing. And now we can do the same thing with the lower bound. Negative 1.645 equals x minus 950 divided by 60. And there you go. So that was 851.3. I know this is just a bunch of random work. If I was a little better about this, I would have organized my work more clearly, but of course, I didn't do that. So with my normal model, I'm going to actually clear this work over here so I can pretend I just got this normal model sitting over here. All right, so the bounds on this is going to be, here's the 950 in the middle. So 1048.7, 851.3, and that will be the bounds for the 90%, the middle 90% of the data. Okay. So most of the other problems don't require this much work to get done, but you can see that there. If you have the Inspire, I believe you have an option for your inverse norm to say, I want 90% area from the middle. Does anyone have the Inspire and has tried that? Anyways, it'll give you either positive 1.64 or 5 and you're negative. I don't have the Inspire, so I don't know exactly what it looks like when you do that. Okay, let's move ahead. I'm not going to go through all these problems necessarily, but I will go through most of them. And I'm going to go through it quickly. If you have questions, you can have me come back to it. Of course, you can jump in, you can chat, whatever you need to do to get my attention. Let me know you have a question. Or if you just want to highlight one, we can come back to it at the end and we can come back. Okay, so the continuous random variable n has a normal distribution with a mean of 7.5 and standard deviation 2.5. Which has a probability equal to 0? Now keep in mind, continuous random variables are ones that you can have any value. It's not discrete like a binomial distribution. It's continuous. Any value is possible. So that means that the actual value, so I have those two right there, but I could find a value of one in between, or the value of one in between those two. And I could keep splitting it and find the value. But the way it works is the actual probability for any particular value is 0, which is a weird thing to say because I do have this value right here. But this is a normal model and the actual particular value has a probability of 0 happening. But what we do have is a probability of less than. So any and all those values less than or greater than a particular value, we can get the area under the curve. But in this case, when we're trying to find the probability that n equals 8, that will be equal to 0. Everything else is fine. Okay. So which is most likely to be approximated by a normal model in these scenarios? So we're looking for one that will be normal. And I'm going to kind of sketch what these look like as we go through. All right, so we've got distribution of number of books read by middle school students where the right tail is longer than the left. Well, that automatically doesn't, let me do a little clearer. Okay, I didn't draw that very well, but that's supposed to be skewed. And so we can see the right tail is longer than the left. Okay, how about lifespan of batteries of a certain size? So most of them cluster around the middle. So we're going to have this kind of mode in the middle, but we got some very low and some very high. So I'm going to have some that are low and some that are high. All right, so off the bat, that one seems normal. Now, the next one, distribution of ages and years of students at a certain college are between 18 and 22, but greater than 22, the ages are spread out more than less than 18. So again, you're going to have like 18 to 22 is going to be where most of your data lives, but then you're going to have some spread out data above 22, not so much below 18. Again, skewed, so I will cross these two off right here. Distribution of number of birthdays per month at a company is approximately equal for each day of a month. So that makes sense. You're going to have a uniform distribution across that month. So that's not normal. And the distribution of length of stay at a hospital, not a hotel, a hospital after surgery. Again, you're going to have some very short stays, but some are quite lengthy. So you're going to have, again, a tail coming off. So the only one from what they're describing that appears to be normal is B. Okay, so just make sure you're reading through and kind of understanding that. All right. So Clara recorded 50 numerical observations on a certain variable. Numerical observations on a certain variable. Okay, wasn't sure what I was reading. And then calculated the mean X bar of the standard and the standard deviation S for the observations. To help decide whether a normal model is appropriate, she created the following chart. Okay, so these values A, B, C, D, and E are going to represent the number of observations falling within those ranges. And what is going to be the best indicator? Wait. Anyways, which of these distributions is correct for the outcome? First of all, we need to have 50 outcomes. I think all these, I'm not going to actually go through. These probably all add up to 50. So let's just say that part's good. But we also know that 68% of the data falls within this range right here. 95% falls in this range right here. And then now for our purposes, it's obviously 99.7%, but if you're talking about 50 data points, we could pretty much assume we're going to get 100% of the data right here, technically 99.7. Okay, so if we've got this, I'm going to figure out, I'm going to approach this mathematically, right? 50 data points, observations, 68% of them should fall in the middle. So I'm going to see what falls in C right here. So if I do that, 50 times 0.68 gives me 34. So in the middle, there should be 34, and it looks like A is my answer because none of these are 34. D is close, but there's too many observations in the middle for that one. So, I mean, at this point, I'd be happy moving on if I had other problems to get to. But of course, we can confirm. Now, if we go to 2 standard deviations out, the B and the D added together with the C, then that, according to this, is 48 observations. So I'm going to do 48 divided by 50 to get 90.96. And of course, we want 95%, so that's pretty close. And the rest of the observations fall outside of that. So A is the answer. Okay, so long story short with this one, we do need to go through and read for certain pieces of information, but we're trying to figure out which of the following best approximates the probability that at least 27% of the children in the sample lived in households that are classified at a particular income level. Okay, so what we are looking at here is that 22% of children in the US under the age of 6 live in households with incomes that are classified at a particular income level. So this is our population proportion, is 0.22. A simple random sample of 300 children. So my sample size is 300. So that was conducted. If the government data are correct, which of the following approximates the probability that at least 27% of the children in the sample, so we're talking about p hat right here, has to equal 0.27, classified at the particular income level. So now I never gave you guys a formal formula for this if you're converting your z-score into what it would look like for proportions, but we can still do this. We know that a z-score is just the value that we're interested in minus the mean divided by standard deviation. Now, we're not dealing with means. We're dealing with population proportions. So what I'm going to do is I'm going to instead compare the sample proportion to the population proportion. So I know it's going to be, if I start plugging numbers in, it's going to be 0.27 minus 0.22. So it looks like D and E can be ruled out. Now the standard deviation, I'll just leave the standard deviation alone, except it's going to be a standard deviation for proportions. And this is one that you'd want to have your AP formula sheet handy. But what you've got is the standard deviation for proportions is square root of P times 1 minus P over N. Now we're dealing with the population proportion when we figure out the standard deviation. So that's going to be 0.22 and then 0.78 is the complement of that, and over 300. So that's going to be my standard deviation. That's what's in the denominator. All right, so the answer here is B. All right, good times. And again, any questions on that, you can stop me if you have them. I'm going to skip this one. This is a pretty straightforward normal CDF calculation. I feel like you guys should be able to handle that. This one is really getting to kind of the concepts behind variability and sample size. So we've got a certain context. 0.325 is the proportion of adults who indicated mystery as their favorite type of book. Anyways, here's kind of the key. There's a sample that's going to be drawn, and sure. Now here's simulation A. We could have 1,500 trials with a sample size of 100. We could have 2,000 trials with a sample size of 50. When we compare these two, what's going to describe the center and the variability between A and B? And just really, really important to note that sampling distributions, regardless of sample size, and remember the sample size will determine the actual distribution, but all of them should fall right on the population mean. Okay, so the sampling distribution mean will be the same as the population mean, or in this case, proportion. Okay, so the centers will be equal, or roughly equal. So A, B, and C have that. D and E, I'm going to cancel out. So now I just need to figure out between A and B, which one is going to have greater variability. And it's an inverse relationship. The larger the sample size, and 100 here is the bigger one, the larger the sample size, the smaller the variability. Remember, in both cases with our standard deviation, we're dividing by n, basically square root of n. So this 100 sample size is going to have less variability. A is going to be less variable than B. So the variability of A will be less than the variation of B, variability of B. There's so many words related to that. Variability, variation, variance, and it can get very confusing sometimes. But anyways, there's your answer. Okay. So we had a simulation set up to figure out the amount of time people spent on a streaming service, and the population average is 210. And so again, a simulation was run, and we ended up with a distribution that looks like this. Definitely not normal. So why is it not normal? And does anyone know why it wouldn't be normal? I know I've conditioned you guys to not having to talk. Okay, so the way that we get a normal distribution, if we're doing a simulation, is we need to have a big enough sample size. Remember, this is basically your large counts condition. N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. So in this case, we didn't do that. We didn't meet that criteria, so we didn't have a big enough sample size. Okay. This is one, I will not put a question like this on the test, but it is, I think, an interesting one, because we've got a distribution here. It doesn't even matter what the distribution is of. And we've got a sample size of 2. And basically they're asking, what would the sampling distribution look like for this population if you've got a sample size of 2? And now we kind of need, this is just a really kind of interesting question. And I want to kind of think of 4 different possibilities here. When I only have 2, and it looks like I have 2 distinct populations right here, that population and that population that are combined together. So I could, if I just call this like population A and B, so I could pull 2 of them from population A. So AA is a possibility, in which case they're going to end up kind of at the lower end. So I'm going to have the average between those 2 be down here. I could have B and B, and then those averages are going to be up here. So I should have some kind of a output with that going on. Now I could have A and B and A. So I'm going to have quite a few that end up average between these 2, so right in the middle, but it also looks like I'm going to have twice as many outcomes like that. So I should have a bigger peak in the middle And so the output of that chart is going to look like that right here. So this is just a real classic way of realizing that if you want to have a normal distribution, then you need to have a big enough N. Okay. Next one. What am I doing here? That's what I'm doing. Okay, we've got a recent report that 90% of adults in a certain region actively try to include vegetables in their diet. A simulation was conducted that consisted of 50 trials with a population parameter of 0.9. Each trial consisted of a sample of 10. Okay, so I can figure out, anyways, the number of successes out of 10 was recorded, and success represented an adult trying to include vegetables in the diet. So I know where the center of this is going to be because I can take my sample size and multiply it by the probability. N times P. This is a binomial distribution. It's going to be the number of successes out of 10. So N times P is the mean for a binomial random variable. And that's going to be 10 for a sample size, 0.9, which gives me 9. So my mean should be around 9. So I can rule out this one. I can rule out this one and this one. Just with that quick calculation, I've got it down to A or E. And the only other thing I need to keep in mind is that each dot represents one trial of 10 sample size. So I should have 50 dots showing that I had 50 samples drawn. And it looks like E has that going on. All right. Another conceptual problem right here. Approximately 52% of all recent births were boys. So that's kind of the probability that we're working with. In a simple random sample of 100 recent births, 49 were boys and 51 were girls. The most likely explanation for the difference between the observed results and the expected results, or we would have expected 52 boys and 48 girls. So the difference is basically just sampling error, or what we call sampling variation. So that is a normal thing, and we should be well aware of that. So nothing to worry about. Researchers will conduct a study of the television viewing habits of children. Let me see something real quick. Okay, no, this one's fine. There was one question from before that I was making sure. I thought I had gotten rid of it. Okay, so they're going to select a simple random sample of children and record the number of hours of television the children watch per week. The researchers will report the sample mean as a point estimate for the population mean. Which of the following statements is correct for the sample mean as a point estimator? So point estimator, just remember, I mean, we're estimating what a specific point is going to be, and that's going to be the population mean. So we're trying to estimate. So if we have a sample size of, anyway, sorry, they don't tell us the sample size. That's in the answer choices. But regardless of our sample size, the sampling distribution mean should be the same as a population mean. So, and regardless of sample size, that doesn't change. So we've got C, D, and E right here saying that one of them is going to be biased, one of them is not going to be biased. And that actually shouldn't be the case. So when you get the entire sampling distribution, they should both be unbiased. But the variability, the bigger the sample size, of course, the smaller the variability. So 25 is going to have more variability than 50. Okay. Now this is some fun stuff right here. We're trying to figure out, when you combine your sample size with your population proportion, what's going to be most likely to produce the greatest standard deviation for sampling distribution of a sample proportion p hat. So we're going to create some kind of a normal distribution out of this. And which one's going to have the biggest standard deviation? If we have a sample size of 1,000, sample size of 100, probability close to 0, close to 1, close to 1/2. So let's kind of think through this. The first thing we know right off the bat is that a smaller sample size will give us a more variability. So I'm going to cross these three off. It's got to be the smaller sample size. But now the question is, does a probability close to 0 give us wider standard deviations, or does a probability close to 1/2 give us wider standard deviation? And you might not know this one off the top of your head. So here's what we can do. I'm just going to calculate what the standard deviation would be, assuming certain things. So if it's close to 1/2, I'm going to assume it's exactly 1/2. 0.5 and 0.5 divided by sample size of 100. There's my standard deviation formula. And that gives us 0.05 as the answer. All right, so now I can do the standard deviation of p hat, the sampling distribution of proportions, when it's close to 0. Now I can't put 0 and 1, but what I can do is I can put something really small. I'll put 0.01 and 0.99. This is going to illustrate for us which one gives us a bigger standard deviation. All right, so now if I do that, I get 0.0099. So the bigger standard deviation is right here. So it looks like when it's close to 1/2, we end up with a bigger standard deviation. And if we really, really want to make sure that that's right, we could try it one more time and compare this one to this 1,000, just because we know conceptually what's right, but we just want to confirm it mathematically. So we could do that 0.5, 0.5 divided by 1,000. And we get 0.016 right here. So, okay, certainly this 0.05 is the biggest we're going to get. All right, so there we go. According to data from the US Elections Project, only 36% of eligible voters voted in the 2014 election. I'm going to take this as a PSA opportunity to say, if you're 18, please vote. All right, moving on. For random samples of size 40, which of the following best describes the sampling distribution of p hat? Okay, so we have a sample size n equals 40. We have a population proportion of 0.36. Let's see, it doesn't really give us anything else, but that's okay. All right. We know that a sampling distribution for proportions, this sampling distribution mean, so I'll just put it this way, is going to equal the population proportion. So this, actually before we answer that, well, I know it's going to be 0.36, so let me just get rid of these two. The other question is it skewed or is it approximately normal? Well, we can check that. This is the large counts condition. So n times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. And I've got 40 times 0.36. This is really the only calculation we need to do to show that. I say that, but just for completeness sake, you'd want to do 40 times 0.64 on your AP test. But obviously, this is going to be the smaller number. So when you do 40 times 0.36, you're going to get 14.4, which is greater than or equal to 10. And you'd get 25.6 right here. So it is going to be approximately normal because it passes that condition. So I'm going to cross that one off as well. It's not going to be skewed. So now the only question we have left to answer is what's the standard deviation? Is it 0.076 or 0.006? And luckily we have a formula for that. The standard deviation of a sampling distribution of proportions is P times 1 minus P divided by N. And that's going to be 0.36, 0.64, divided by 40, and that'll give us the last piece of information we need. .076. So there's the answer. All right, I am going to skip this one. You can hopefully tell just from the answer choices, this is going to be more of the same, like figuring out what calculation to do. But you can read the context later. You can figure out which calculation is correct for this particular problem. And same with this one. I'm going to skip this one also. But if you want to come back to see these at the end of class, you can ask and we'll come back and look at them. We'll do this one though. Okay, based on records kept at a gas station, the distribution of gallons of gas purchased by customers is skewed right with the mean of 10 gallons and the standard deviation of 4 gallons. All right, so we've got something that looks like this. Mean, well, the mean's not going to be right there, but wherever the mean is 10 gallons with a standard deviation of 4. All right, we didn't have to draw that, but it's good to get a visual on it. A random sample of 64 customer receipts was selected, and the sample mean number of gallons was recorded. And this process was repeated 100 times. So we got 100 samples of 64 receipts each. And which is the best description of the dot plot that is created from these 100 samples? All right, now, one thing that we did not talk about, so I wouldn't put a question like this on the test, but one thing that is important to recognize if you had this knowledge is that we need to know if this is going to be normal or skewed. We did not talk about how you determine normality for means. We said it needs to be a big enough N, and I'll go ahead and tell you now, we're going to come back to this. This is not something you need to know for the test. To determine if it's a big enough N there, you want to have at least a sample size of 30. So if you have any statistical knowledge that you learned in the past, you might have heard about like having a sample size of 30 is an important thing. There are other ways you can do this even if you have a smaller sample size. So we'll get to that more later. But this is means we have 64 in each sample. We can consider it normal. So I'm going to cross these 3 off. It will be approximately normal. Now we just need to determine what is the standard deviation of this going to be. And the standard deviation for our means is going to be the population standard deviation divided by the square root of n. So that's 4 divided by the square root of 64. 4 divided by 8 is 0.5. And there it is. The mean doesn't change, of course, so we're good with that. All right, I think we only have 2 more questions to look through. And with this one right here, it's asking us what's the best estimate for this standard sampling distribution of X bar. Okay, now the way that you look, okay, wait a second. I might have read this one wrong earlier. So I need to make sure that I'm looking at this right. We've got a sample size of 25. So we want, which is the best estimate of the standard deviation of the population? They're not asking for the standard deviation of the sampling distribution. So when I was going through this before, what we can recognize is that the standard deviation right here is going to be at this inflection point where it kind of stops decreasing rapidly. And the rate of decreased changes. And that's about 15. All right. We're looking for our best estimate here. So 15 equals the population standard deviation divided by the square root of n. So 15 equals this divided by the square root of 25. So now I can take this square root of 25 and I want to multiply both sides by 5, which gives me 75 for the population. Okay, now I said 15 before because I didn't read the question closely. It is asking for the population. So that is our approach here. Okay, so good times. And the last one we're looking at here, it's really hard to read this one, but the population distribution of random variable X has a mean of 85. So I'll write this big enough for everyone to read. And a standard deviation of 18. Then we have a sample size of 40, so we're going to do that. And which of the following graphs is a sampling distribution of the sample mean X bar from sample sizes of 40? Okay, so the first thing that we know is that the mean of our means is going to be equal to the population mean, so it's going to be 85. I can cross off anything that doesn't have a mean of 85, which is D, E, and that's about it. The other thing, and this is what we just talked about today, so it's not like you had this knowledge before, our sample size is greater than, not 10, sorry, that's a large count, greater than 30. Our sample size is big enough, it should be approximately normal. So I'm going to get rid of the skewed one right here. So now I just need to figure out the standard deviation. Which one has the correct standard deviation? So the standard deviation for our sampling distribution of means is going to be the population divided by square root of n. So that's going to be 18 divided by the square root of 40, which is 2.846. And because we're not doing anything super exact with this, I'm going to say it's approximately 3. All right. So if I look at my two options, B and C, I'm going to start with this one. Here's the mean, 85. If I go out 3, it's going to be like to right here for one standard deviation. And I can see that is not what's going on in that histogram. We are not seeing a standard deviation of 3. It's much smaller. But if I go out here, here's the mean, and this is showing the standard deviations. That is much more believable as far as the standard deviation go. So that is going to be our answer. Okay. And that's the last one that we were looking at today. We actually are ending 45 minutes early, but let me go over this real quick. Again, 60% of your test is just going to come from completing the AP Unit 5 Progress Check Part A, which is, there's an assignment for it in the classroom. So make sure that when you do the progress check, you actually just submit the assignment saying that you got it done. It's going to be graded by AP, and I'm going to see the results, but I'm only going to grade it to make sure that you completed it. And part 2 is going to be 10 multiple choice questions tomorrow, and they will be based on questions that we looked at today. We didn't go over every question, so I encourage you to go over these questions tonight for review. And that is what you'll take tomorrow. So just to make sure it's really clear, if you only get 5 of the 10 correct tomorrow, you got a 50%. Well, it's 50% of the 40 points that you could have got. So 50% tomorrow translates to an 80% on the test, assuming you do the progress check. This should be a good grade for everyone tomorrow, just to kind of end on a good note before you do that midterm on Friday. All right. And there you go. The remaining 40% comes from that. So if you are satisfied with your care today, you can have yourself a wonderful day. If you have more questions, please feel free to stick around and I will help you out. All right. Have a good one, guys.